Hello, everyone, and welcome to This Explainer. Today, we're going to decode something that honestly looks like pure magic, but is actually just fundamental physics. We are diving into how light travels, how it bends, and how it sometimes gets completely trapped, totally tricking our eyes in the process.
To get us started, picture something you've probably seen 100 times. You're sitting by a pool, or maybe you just have a glass of water in front of you, and you dip a straight stick, or a straw, right into it. Suddenly, exactly at the waterline, that stick looks completely broken or sharply bent, right? So why does that happen? It's a classic real-world magic trick. But as we'll see today, our eyes aren't broken at all. They're just reporting the exact behavior of light as it navigates different environments. Now, our grounding source material today is this pretty detailed physics syllabus covering the refraction of light. I know, at first glance, it looks like a dense wall of text and math symbols. But don't sweat it, we're going to extract the exact concepts and formulas hidden in here and turn the whole thing into a crystal clear, highly visual roadmap. Here's our game plan for this explainer. We've got 5 specific missions. First, the magic of bending light. Second, the rules of refraction. Third, real versus apparent depth. Fourth, total internal reflection. And finally, prisms as perfect mirrors. All right, let's dive right into section 1, the magic of bending light, and figure out exactly what refraction actually is. So, refraction occurs whenever a light ray changes medium. Imagine light traveling through the air and suddenly, bam, crashing into water. When it hits that new boundary, 2 things happen. You get partial reflection, which bounces some of the light back, and refraction, which actually bends the light that passes through. Now, there are specific conditions for light ray to pass entirely undeviated, meaning it doesn't bend at all, but that usually only happens if it hits the surface perfectly dead on. For the most part, when light switches mediums, it bends. Okay, moving on to section 2, rules of refraction. Let's look at the actual math behind this magic. To really understand this, we use a beautifully simple formula for something called the refractive index, which is represented by the Greek letter mu. The formula is simply mu equals c divided by v. But what does that actually mean? Well, it's just the speed of light in a vacuum, which is a constant, c, divided by the speed of light in whatever specific material you're looking at, which is v. Think of this index as a measurement of exactly how much a specific material slows light down. So, what happens to the properties of light when it enters that new medium? We can see this in a really simple equation, v equals f times lambda. When light bends, its speed, v, and its wavelength, lambda, absolutely change. However, there is one thing that remains completely locked in, and that is the frequency, f. Literally, no matter how much the light slows down or shortens its wave, its frequency stays perfectly constant. And these values shift dramatically depending on the substance you're dealing with. Light travels absolutely fastest in a vacuum, and then it slows down successively as it hits air, water, glass, and finally, dense diamond. Because diamond has such an incredibly high refractive index, it slows and bends light dramatically. And you know what? That is exactly why diamonds sparkle so brilliantly. Let's bring this into the real world with section 3, real versus apparent depth. This concept perfectly explains that broken stick illusion we opened with. It all comes down to the difference between real and apparent depth. Real depth is just the actual physical location of the object. But because light rays bend as they leave the water to reach your eyes, your brain gets totally tricked. It projects those rays back in a straight line, creating an apparent depth that bends the stick upward. It's the exact same reason a swimming pool always looks shallower than it actually is. And you've likely noticed other everyday applications of this too. Take lateral displacement. When light passes through a rectangular glass block, the ray exits parallel, but it's physically shifted to the side. Or how about the weird phenomenon of seeing multiple ghost images in a really thick glass mirror? That's just the partial reflection and refraction we talked about earlier, creating faint echoes of light behind the main reflection. All right, on to section 4, total internal reflection. I like to call this the point of no return. Up until now, light has just been passing through the boundary, bending as it goes. But what happens if it literally can't get out? This brings us to a super fascinating threshold called the critical angle, or C. This is the exact angle of incidence where light, trying its hardest to escape a dense medium, bends so much that it just travels perfectly parallel, skimming right along the boundary surface. And the math linking our previous section to this one? It's right there. The refractive index, mu, is equal to 1 divided by the sine of the critical angle. Now, for this perfect trap to actually work, two golden rules have to be met. First, the light must be traveling from a denser medium, like glass, and trying to escape into a rarer medium, like air. Second, the angle must actually exceed that critical angle we just defined. When both of these conditions are met, boom, the boundary acts like a perfect mirror, and 100% of the light is reflected back inside. It is completely trapped.
Which brings us to our final stop, Section 5, Prisms as Perfect Mirrors, where we learn how to trap light on purpose.
To really harness this trapping effect, we don't just use any random piece of glass. We use specific triangular glass prisms with exact angles. The syllabus points out 3 specifically: the equilateral at 60-60-60, the standard right angle at 60-30-90, and the isosceles right angle prism at 45-45-90. So why do we need these exact shapes? Well, by utilizing right-angle prisms, we can obtain very specific, deliberate light deviations. We can actually force a beam of light to turn a perfect 90-degree corner, or even do a complete 180-degree U-turn. It's essentially hacking the physics of light to create perfect directional control.
Ultimately, you might be wondering, why use a prism instead of just a regular mirror? It all comes down to efficiency. A standard plane mirror, with its silvered backing, will always absorb a little bit of light. But total internal reflection inside a perfectly angled prism, it is virtually 100% efficient. So in a way, it is a much more perfect mirror than a mirror itself.
And that brings us to the end of our roadmap. We've broken down exactly how light bends, slows down, and gets completely trapped. But honestly, it leaves us with an amazing final thought to ponder. If understanding these incredibly simple mathematical rules of refraction allow us to completely decode everyday illusions, like a bent stick in a glass of water, what other realities around us are really just tricks of the light waiting to be understood? Keep observing, keep questioning, and thank you so much for joining me for this explainer.